As she said, my name is Trevor Torpin, and I'm a graduate student in the physics department, and I'll be presenting today on UED theory and calculating cross-sections. So first off, what is dark matter? Dark matter is matter that is believed to exist due to its gravitational effects on visual matter. It's non-luminous, meaning it doesn't interact or emit or reflect light. It actually makes up the majority of mass in the universe, and you can see here on this pie chart, which is kind of the energy content in the universe, that physicists believe that 74% of the universe is made up of dark energy, and then 22% is made up of dark matter, and only 4% is made up of atoms, which is the normal everyday stuff that we're familiar with. Its current composition is unknown, and there's many different theories on what it exactly is, but there hasn't been any significant proof on what exactly it is. But there is substantial evidence for dark matter via the galaxy rotation curves or the Big Bang nucleosynthesis. And there's three possibilities of ways to detect this. We can hope to produce it in particle accelerators, and hopefully we'll see that at the Large Hadron Collider in CERN here soon. We can hope to see it directly just via a detector, and some of these experiments are CDMS, Cogent, and DAMA, and I'll be concentrating on this one with my talk. And there's also, you can detect it indirectly and by observing decay products from dark matter annihilations, because they annihilate with each other. Some experiments for that include the Fermi Gamma Ray Space Telescope. Now, direct detection, it relies on the fact that there's a large number of WIMPs, which WIMPs stand for a weakly interacting massive particle, and it's kind of the generic term for the most likely dark matter candidate. And so a large number of these pass through the Earth every second. And these direct detectors rely on measuring the nuclear recoil when a dark matter particle will collide with a target nucleus within the detector. And now that's a picture of the detector at Cogent, and these detectors must be radioactively clean and shielded from other particles, so they're usually buried in mines deep underneath the ground to kind of reduce the background radiation. So we're trying to reduce that as much as possible to get as clear a signal as possible. Now, what is universal extra dimensions theory? It's essentially a modern Kaluza-Klein theory, and this dates back to the early 1900s with Kaluza-Klein theory. The big push back then was unification theories, and it still is a big push now with trying to search for a grand unified theory of uniting all the forces. And so what Kaluza and Klein did was that they attempted to unify the forces of gravity and electromagnetism, and they accomplished this by adding an extra dimension. And what Kaluza showed was that gravity in 5 dimensions is mathematically equivalent to gravity in 4 dimensions plus electromagnetism. Now, UED theory was first proposed in 2001 by Appelquist, Chang, and Dobriscu, and it's different from other modern theories because it allows all the standard model fields to propagate in these extra dimensions. And the reason we don't see this extra dimension is that it's basically compacted along this orbifold, meaning it's very small so you just can't see it. And one really exciting thing about this theory is that it naturally contains a dark matter candidate. These candidates gain mass the exact same way as Kaluza's original theory, where you get an excitation of standing waves, and that just keeps increasing the mass of these particles. And so what you eventually are left with is you get standard model particles and then a tower of higher dimensional excited particles above that. And the mass scales according to 1 over r, where r is the size of this extra dimension. And through a thing called KK parity, it keeps the lightest Kaluza-Klein particle stable. And normally these really heavy particles will decay because they're generally unstable, but because it's parity, it's stable, so that'll be our dark matter candidate. Now, but what particle that we can see here would be the LKP, the lightest Kaluza-Klein particle. And so physicists Chang, Machev, and Schmaltz developed a KK particle spectrum shown here, and their theory had 2 main parameters: r, the size of the extra dimension, and lambda, the cutoff scale of the theory, where it stops being effective. And now what they found is that the first excitation of the photon would be the lightest Kaluza-Klein particle, and they called it the B1 particle. Now what my research actually deals with is that a direct detection experiment called CDMS, which is located in a Sudan mine in Minnesota, and they just recently released their data, and they found 2 possible detections. Unfortunately, that's not quite enough to see a say specifically that is a dark matter interaction, because there's a probability of 23% that is just background events. But their data is still useful, and they are used to improve the limits on the WIMP cross-section. And here is a graph of their cross-section versus the mass. And basically these are known as exclusion curves, and anything above those lines are excluded from being a dark matter candidate because we would have already seen it by now. Basically, I will use their data to constrain R and lambda from UED theory and find out what parameters for UED theory must have to fit the CDMS experiment. Now, in order to constrain R and lambda, I will need to analyze these cross-sections. And basically, a cross-section is just a likelihood of an interaction between particles. And I will work on this program already started by another graduate student that will calculate these cross-sections for me. But to calculate cross-sections, we have to analyze what are called Feynman diagrams. And here is an example of a UED Feynman diagram of two dark matter particles annihilating with each other and producing two gamma rays. These diagrams can get quite complicated, and so far I've been working on calculating QED, quantum electrodynamics, and other weak interaction cross-sections. That's kind of to make sure I know how to do this first. Now, to do this, quantum electrodynamics is kind of the relativistic quantum field theory for electrodynamics, and basically it describes how light and matter interact. It's governed by the Dirac equation here, which is kind of the relativistic equivalent of the Schrodinger wave equation in regular quantum mechanics. And these describe particles of spin 1/2, or fermions. And the wave function psi is now a four-component vector. And now we'll have these gamma matrices, which run, there's actually 4 of them there. And they run through the polyspin matrices. And these are quite complicated, but luckily, using Feynman diagrams, we don't really have to worry about that so much. So these diagrams allow us to calculate probabilities of reactions between elementary particles. And each diagram has an amplitude m associated with each one of them, and that is used in the calculation of cross-section. Here is an example of electron-electron scattering, where 2 electrons just come in, interact with, and exchange a photon, and then leave again. Now, to calculate these cross-sections, you have to go through what is called the Feynman rules. And so to do that, it's actually fairly straightforward once you've worked a few of these. But what you do is you start out with each line, each particle coming in, you give it some sort of a momentum p, and then you draw what direction it's moving in forward in time. And then for each internal line, like the photon in the previous diagram, you just give it a momentum q. And then these external lines also add a factor, depending on what particle it is, of spinners, which are used in the Dirac equation. You just look them up in the table. And then each vertex will contribute a factor of I, G, times the gamma matrices, where G is just a dimensionless coupling constant related to the charge of the electron. And then each internal line will also contribute a factor known as a propagator, and depending on what particle is being exchanged. There is a propagator for the electron-positrons, and then for photons beneath it, which if we would have used the photon propagator in the electron-electron scattering event, where that G mu V is just the normal metric. Now, at each vertex, you also write down a delta function in this form where k represents the momentum going into the vertex, and then a negative k if it's leading it. And then for each internal momentum, you write down a factor of d with the internal momentum, and then you just integrate. Now, after you're integrating, you're left with another delta function, and this represents the overall energy momentum conservation. And all you have to do is just cancel it and multiply the whole thing by I, and then what you have left is just the amplitude of the diagram. And one thing you also have to be careful for, if you have more than one diagram involved in the process, you have to include a minus sign if it differs by more than 2 incoming electrons, because the fermions are antisymmetric. Now, some general notes about this is that it's very important to follow the correct order of these rules, because otherwise the math will not work out. And the best way to do this is to follow the fermion line backward through the diagram and writing the factors down as you come across them. And each line will have an adjoint spinner, a 4x4 matrix, and another spinner. And each vertex will actually carry a contravariate vector index that will contract with the covariant index of the associated photon line of a propagator within it. Now, weak interactions are governed by what's called GWS, or stands for Glashow-Weinberg-Salom electroweak theory. And here it's a little bit different. The mediators here, instead of the photon in that electron-electron scattering, are actually the charge W in plus minus bosons and the Z0 boson, which is neutral. And these are quite a bit more massive, so they govern the weak force, which works over a very much shorter distance than the photon. The propagator is shown there, but luckily we're usually looking at momentum, which is much less than the energy that we're interested in. And so we're able to use this simplified propagator there. For now, the vertex factors will also change. You have to be careful what particles you use. You use the top one for the leptons, and then the middle one you actually use for the quarks, because you can't just model like a proton with a proton. You have to include each proton is made up of 3 different quarks, and you'll be using this where the Vij stands for the CKM matrix, which are experimentally verified. And then also for the Z boson, it's neutral, so it's a little bit more complicated. And you have the CV and CA constants, which you can just look up in a table and use in your calculations. Now, once you go through all these Feynman rules, that'll give you the amplitude, which you can use to calculate the cross-section. And so it's kind of a long process. But then once you have that, you can finally use it to calculate the cross-section, which is here, which is given by the sigma is the cross-section. The capital omega is the solid angle that you're kind of examining. And then you have a bunch of constants, and then you have S, which represents a statistical factor, because when you do this, you'll get double counting. And so you get a factor of 1 over S factorial for each group of particles that you're looking at. And then N is actually the average amplitude, and then you have your energies, and then the momentum going through. And once you do all this and all the integrating, then you'll have your cross-section. So these are actually quite long calculations. Now, as I said, it's quite a long process, but it's actually fairly straightforward after you work through several examples, and I don't have time to go through one of those with you. But fortunately, computers can calculate the cross-sections for us much faster than we can. And so kind of my next steps is I'll be finishing up this program that another graduate student wrote, and we'll start calculating these cross-sections to constrain the UED theory. So with that, here are a few of my references. And then I'd like to thank Dr. Duda and the Astro Particle Research Group at the Physics Department. Are there any questions?